Hey everyone, welcome back to the channel Code with AKJ. Today is day 48 of solving LeetCode 75 challenge, and today we are solving a very interesting problem called routing oranges. It involves grid traversal and simulating how the route spreads inside a matrix. So if you enjoy coding content like this and want to stay updated with the daily problem solutions, so don't forget to subscribe to the channel and hit the bell icon so you never miss an update. So let's dive in. The problem statement says you are given a m cross n grid where each cell can have one of the three values: 0 representing an empty cell, 1 representing a fresh orange, or 2 representing a rotten orange. So every minute any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1. So we have given a 2D matrix of size m cross n, and each cell in this grid can have three values, that is 0, which represents empty cell, 1 represents a fresh orange, and 2 represents a rotten orange. And every minute a rotten orange infects any adjacent fresh orange in the up, down, left and right directions. And our task is to find the minimum time in minutes that must elapse until no cell has a fresh orange. So if it is impossible, we will return -1. So let's quickly understand this problem statement with these three examples. So in the example 1, at index 0, 0, we have a rotten orange, and we need to find the minimum number of minutes this rotten orange will take to rot all these fresh oranges. And after going through all the directions, and if there are still fresh oranges inside the matrix, then we'll return -1. So in first minute, we'll go through four directions, that is up, left, down and right. Since up direction goes out of bound and left direction goes out of bound, we have two directions left, that is down and right. So we have two fresh oranges in both the directions. So in first minute, we'll rot these two fresh oranges. Coming to the second minute, we have three rotten oranges, and we'll check the adjacent cells of these three rotten oranges to find our fresh oranges and rot them. So for this particular rotten orange, we have two adjacent fresh oranges. Up goes out of bound and left is already rot. So we'll left with two directions, that is right and down. So we'll rot those two fresh oranges as well in second minute. And coming to the third minute, we'll again check whether we have fresh oranges or not. So we have fresh oranges too. If we consider all the four directions for this particular rotten orange, since the up and left is already being rotten, and the only direction we have left is down, and we have fresh orange in the down direction, so we'll rot in the third minute. And coming to the final minute, we have for this particular rotten orange, only direction we have fresh orange is the right direction, so we'll rot that fresh orange in the fourth minute. And after finishing this operation, there are no fresh oranges left in this grid, and we'll return the number of minutes to rot all these oranges. And for this given example, our answer would be 4. So it took 4 minutes for this rotten orange to rot all these fresh oranges, which is in 4 minutes. Coming to the second example, we have 2, 1, 1, 0, 1, 1 and 1, 0, 1. So let's quickly draw the grid of this given example, and let's understand and calculate the number of minutes. So here's the diagram for our second example. So we have a rotten orange at the 0, 0 cell. So let's quickly write the index values. So we have a rotten orange at this given index 0, 0, and we need to find the minimum number of minutes to rot all these fresh oranges. Let's quickly represent these values. So 2 represents a rotten orange, 1 represents a fresh orange, and 0 represents an empty cell. And we have to go through all the four directions: up, down, left and right. So our first step here would be to check its adjacent index value. So up goes out of bound, left goes out of bound, and down we have an empty cell, and towards right we have a fresh orange. So in first minute, our grid changes in this way. So the 1 becomes 2 here in the first minute. And in second minute, we'll again check for all the rotten oranges whether we have a fresh orange in its adjacent cell or not. So for this orange, we'll check its four directions. So the up direction goes out of bound, the left direction the orange is already been rotten, and when we see its down and right direction, there are two fresh oranges. So we'll rot these two fresh oranges in the second minute. So in the second minute, our grid changes something like this: 2, 2, 2, 0, 2, 1, 1, 0, 1. So in 2 minutes, this particular rotten orange have been rotten all these three fresh oranges. So coming to the third minute. So for this given rotten orange, we'll check four directions. The upper direction is already been rotten, and the left direction we have an empty cell, and down direction we have an empty cell, and coming to the right direction we have a fresh orange. So we'll try to rot this fresh orange. So the grid changes in this way. So in the third minute, it again rotten a fresh orange. So coming to the fourth minute, we'll again check all the four directions and try to find whether we have a fresh orange in its adjacent cell or not. So for this given rotten orange, the left direction is already being rotated, the up direction is already being rotated, and coming to the down direction, we have a fresh orange. So we'll try to rot that fresh orange. So this one becomes 2 in the fourth minute. Coming to the fifth minute, if we consider this rotten orange, we'll check all the four directions. Since all the oranges are being rotten and there's an empty cell here in the left direction, we'll stop our loop, which means there was no change in this given search. After stopping our process, we'll again check whether the given grid has any fresh oranges left or not. So in this case, if we search inside this grid, we have a fresh orange here left after doing the whole process. So we were not able to rot all the fresh oranges in this case. So for this given example, we'll return -1s because it was impossible to reach this given fresh orange through any of this rotten orange. So this was the example 2. So again, let's take the example 3. In example 3, we have a single row and 2 column where we have an empty cell and we have a rotten orange. Don't have any fresh oranges in this given grid. We'll directly return 0 as there are no fresh oranges present inside our grid. So this would be an edge case where if the number of fresh oranges inside our grid before starting the process is 0, then we'll return 0. This would be our problem statement, and while understanding this problem statement, we have also gone through the brute force approach where we try to rot all the fresh oranges by checking all the four directions, and for every minute we'll try to check whether for that particular minute we were able to rot any fresh orange or not. So if we were able to rot any of the fresh orange, then we'll continue the process, and if at any point we were not able to rot any of the fresh orange, then we'll stop our condition, and after finishing that condition, we'll check whether this given grid has any fresh oranges left or not. So if it is left, then we'll return -1, which means we were not able to reach that fresh orange through that rotten orange. There are no fresh oranges, then we'll return the number of minutes. So that would be our brute force approach. So let's quickly go through the time and space complexity of this brute force approach. So the time complexity of this brute force approach will be m cross n square, where m and n are the size of our rows and column of the grid, and whereas the space complexity would be O of m cross n. So in our brute force approach, we are creating a copy of the grid for each and every minute, and we are traversing the grid to find all the rotten oranges, and for each rotten orange we are trying to find all its four directions since we are moving in all the four directions. And if no fresh orange gets rotten in a round, some are still left, then we'll return -1 as in this given example. So we are repeating this process until or unless all the fresh oranges are rotten, and finally we are returning the number of minutes if all the fresh oranges are rotten. So since we are repeating this whole process until or unless fresh oranges are being rotten, and we are also creating a temporary grid each time, that is the reason we have a space complexity of O of m cross n. And since we are using a condition while loop, and inside the while loop we are again using two for loops to check inside the grid to find all the rotten oranges, and for each rotten oranges we are trying to check all the four directions, hence the reason O of m cross n whole square. So let's quickly go through the code and let's submit. So here's the code for our brute force approach. Here I have taken the size of both row and column and stored it in the variables m and n. I've also taken the variable time, which would be initially 0, taken a variable changed, which would be initially true, like assuming the orange will rot in the first round itself, and we'll run a loop while of true until or unless we'll rot all the fresh oranges inside our grid. So the change would be false for each and every round. So we are creating a temporary grid, copying the actual grid inside our temp variable, and we are checking for each and every rotten orange to its all four directions. If we found a rotten orange, we'll try to rot all its neighbors by checking in all the four directions, that is left, right, up and down. So after checking all its neighbors and rotting the fresh oranges, if this change variable becomes true, which means we have rotten the fresh orange, update our grid, and we'll continue with our next process by incrementing our time variable. So this happens for first round. So in the same way, we'll try to check for each and every rotten orange in each and every round and we'll rot all the fresh oranges until or unless all the fresh oranges becomes rotten. If at all our change variable becomes false in any of the round, which means we haven't rotten any orange in that particular round, stop our while loop and we'll do a final check inside our grid whether if any fresh orange remains inside our grid or not. So if it remains, it means we haven't reached that particular fresh orange through this process and will return -1. And if we didn't found a fresh orange inside our grid, we'll return the number of time it took to rot all these fresh oranges. So we'll return time at the end of our code. So let's run this code. It's working, so let's submit. As you can see, this gives a successful submission, but it is highly inefficient for the bigger grids as the time complexity of this approach is very high. So let's quickly go through our optimal approach where we'll try to use the BFS approach to store all the rotten oranges inside our queue and we'll process each and every rotten oranges one by one. So now let's solve this problem optimally using breadth first search approach. So here the idea would be to treat rotten orange as the source and we'll run a multi-source BFS from all the rotten oranges simultaneously and we'll track the time at the BFS level. So we'll consider this rotten orange as a source and we'll try to process from here with the help of our queue. And for every rotten orange processing, we'll track the time it took to rot all the fresh oranges. So the steps for our optimal approach where we are using a multi-source BFS would be, the first step here would be to traverse the grid and we'll push all the rotten oranges inside our queue. So we'll take a queue and we'll push all the rotten oranges, the index of these rotten oranges inside our queue with the time initially 0. And we'll initially also count the total fresh oranges to handle our edge case where if there are no fresh oranges initially, then we'll return 0. So while pushing the rotten oranges inside our queue, simultaneously we'll also count the fresh oranges inside our grid and we'll check if the fresh orange count is 0, then we'll return 0. Our third step here would be to do the BFS traversal. So for each rotten orange present inside our queue, we'll rot its adjacent cell that is going through all the 4 directions. And if we found any fresh ones, we'll rot that and we'll reduce our fresh count parallelly. Our fourth step here would be to keep track of maximum time taken. And our fifth step, that is at the end, we'll check our fresh count. That is, if fresh count is 0, we'll return our time, and if not, then we'll return -1. So let's quickly do a dry run on this given example to understand our optimal approach where we are using multi-source BFS, considering each and every rotten orange as a source and rotting all the fresh oranges by going through the adjacent cells, that is in 4 directions. So our first step here would be to take a queue and traverse the grid and push all the rotten oranges inside our queue. So in this given grid, we have only one rotten orange that is present at index 0, 0. So we'll push the 0, 0 inside our queue. We'll also take a time variable which would be initially 0 and also the fresh count here, which would be in this case 1, 2, 3, 4, 5 and 6. So our fresh count here would be 6. Our timer would be 0 initially and we have pushed our rotten orange inside our queue which is 0, 0. We'll start our BFS traversal. So we'll pop this particular index from the queue and we'll check all its 4 directions. So its 4 directions would be up, down, left and right. If we consider the up directions, it goes out of bound, so we'll neglect this direction. If we move towards left, again it goes out of bound of the grid, so we'll neglect this direction as well. If we consider the right and the down direction, we have found a fresh orange in these 2 directions. So at minute 1, our grid becomes something like this, where this particular rotten orange presented 0, 0 will rot 2 fresh oranges towards its right and down. The timer becomes 0 to 1. We have rotten 2 fresh oranges, will decrement our fresh count from 6 to 4. There are 2 rotten oranges. Push these 2 index values inside our queue. So the index values of these 2 newly rotten oranges would be 0, 1 and 1, 0. So again we'll pop the front value. So the front value would be 0, 1, that is this particular orange. Again go through all the 4 directions. We have again 2 fresh oranges in its down and right directions. It will rot 2 new fresh oranges. So the grid becomes 2, 2, 2, 2, 2, 0 and 0, 1, 1. So timer becomes 2. And since we have rotten 2 new fresh values, so the fresh count would decrease from 4 to 2. And now we'll push these two newly rotten oranges index value inside our queue. So the index values would be 0, 2 and 1, 1. We'll take the front value of the queue 1, 0. We'll go through all the four directions, and since there are no fresh oranges for this particular rotten orange, we'll move on to the next source, that is 0, 2, which is this given orange, and we'll again check all its four directions, and since there are no fresh oranges for this given rotten orange, we'll move to the next source value, that is 1, 1, which is this particular orange. We'll go through all its four directions, and for this given orange we have a fresh orange in its downward direction, which is this particular index, which is 2, 1. So for this given source we have found a fresh orange, and we'll rot this orange by incrementing our time. So at minute 3 our grid changes from 222 220011 to 220021. So at this particular level, our time 3, we have rotten a new fresh orange, and since we have rotten a new fresh orange, we'll decrement our fresh count as well from 2 to 1, and we'll push this particular index inside our queue. So our queue contains the only index 2, 1. So for the next processing, since we have already incremented our time 3, we'll pop this particular index and we'll go through all the four directions, and since we have found a new fresh orange towards its right direction, so we'll increment our time variable, that is from 3 to 4. We'll rot this new fresh orange as well, and our final grid would look like this, where the values would be 222 220 022. So since we have rotten a new fresh orange, we'll push this particular index value inside our queue. So our queue index becomes 2, 2. Our fresh count decreases from 1 to 0. For the final processing, we'll pop this particular value from our queue, and we'll go through all its four directions, and since we have no fresh oranges left, we'll stop our processing. And now the queue becomes empty. So since our queue becomes empty, we'll stop the process, and now we'll check our fresh count. So here, since the fresh count becomes 0, which means we have rotten all the fresh oranges, so we'll return our time. In this example, our time was 4. So in 4 minutes, we were able to rot all the fresh oranges inside our grid. So this was our optimal approach. So let's quickly go through the time and space complexity. So the time complexity of this approach would be O of m cross n, as we are traversing through the grid only once. And coming to the space complexity, the space complexity would be m cross n, as well, as we are using queue to store all the index values of our grid. So in the worst case, if all the index values are the rotten oranges, then in that case we need to push all the rotten oranges inside our queue, which would be O of m cross n. So let's quickly code this optimal approach and let's submit. So let's quickly code our optimal approach, where we are using multi-source BFS and going through all the four directions and trying to rot all the new fresh oranges. So initially I'll take both the row size and column size. I'll also take the time variable, which would be initially 0, and the fresh count, which would be initially 0. And since it is a BFS approach, we'll use a queue, and since we are storing the index value of our rotten orange, we'll take the queue in the form of pair of int, 8. So our first step here would be to traverse through the grid and push all the rotten oranges inside our queue, and parallelly also counting the fresh oranges. So if grid of I and j is 2, it means we have found our rotten orange and we'll push that inside our queue. Else if grid of I and j is 1, which means it is a fresh orange, we'll increment our fresh count. We'll handle an edge case where if the fresh count initially is 0, we'll directly return 0. So if fresh is 0, we'll return 0. I'll try to store all the four directions inside our two vectors. So these two arrays would store all the x and y directions in all the four directions. So now we'll start our BFS traversal. So our condition would be until or unless this queue becomes empty. For each and every processing, first we'll increment our time variable. Now we'll grab the size of our queue, and until or unless this queue size becomes 0, we'll perform a set of operation. So the first operation here would be to grab our first index, the front value of our queue, with the help of queue.front, and we'll pop the index from the queue. So the current I would be the current dot first, current j index value would be current dot second. And now for this current I and current j value, we'll try to check all the 4 directions with the help of for loop. And now we'll calculate the new I value, which is the current I plus the direction of x, and the new j value, which is the current j value plus the y directions of k. And now we'll check whether this current index value goes out of bound of the grid or not. And if it is inside our bounds, then we'll check whether this current index value has a fresh orange or not. So the conditions would be new I should be greater than or equal to 0, new I should be less than r, new j should be greater than or equal to 0, and new j should be less than c, as well as the grid of new I, new j should be equal to 1, which means it should be a fresh orange. So if it satisfies all these conditions, then we can say that we have found a fresh orange in its adjacent cell. We'll decrement our fresh count and we'll push this particular newly rotten orange inside our queue. It is new I and new j. This would be our set of operation for each and every round, and for each and every processing we'll increment our time variable. After finishing this and checking all the 4 directions, we'll check if our fresh count becomes 0, which means there are no more fresh oranges present inside our grid, then we'll return time. And after finishing all these, if there are still fresh count variable, then we'll return -1. So let's run this code. It's working, so let's submit. As you can see, this gives a successful submission. So the time complexity of this approach would be O of m cross n, and the space complexity of this approach is also O of m cross n, which is highly efficient for bigger grids as well. So let's quickly go through the time and space complexity analysis of this given problem statement. So in our brute force approach, we were trying to check for each and every rotten orange, and we were trying to process by going through all the adjacent cell, and we were using a change variable which would check for each and every round whether we were able to rot a fresh orange or not. And in the same way, we were checking each and every rotten orange separately. So in the worst case, the time complexity of that approach was O of m cross n whole square, and the space complexity was also O of m cross n, as we were trying to create a separate grid. We were trying to copy this grid and processing for each and every round. Hence, the space complexity of our brute force approach was O of m cross n. Whereas in our optimal approach, where we have used multi-source BFS approach, where we were considering each and every rotten orange as a source. So with the help of this particular method, we have brought down the time complexity from O of m cross n whole square to O of m cross n. Whereas the space complexity was O of m cross n as well, as we were using Q. So that would be our time and space complexity analysis. So that's it for today. If you're finding this explanation helpful, make sure to hit the subscribe button so you don't miss out on more such daily coding content. So we have started with a brute force idea, but realized it's inefficient for bigger grids. And then we have moved on to an optimal BFS solution, where we have understood how plot spreads level by level. So this is a classic grid plus BFS problem and a favorite in interview for testing how you model problems. So thanks for watching till the end. If this helped you understand the rotting oranges problem, please leave a like, share it with your friends. And of course, don't forget to subscribe for more daily coding explanations. I'll see you in the next video. Thank you.